So we haven't done any work there. Well, yeah, we haven't done any work there really. Well, have we? Oh, okay. We've done some work, but it's not ready to be talked about. There you go. So I'm talking about work that's arisen from my team at the University of Oxford. And over the years, we've had sort of various bits of funding from various people along the way. Okay, so this is what we're going to consider. At the beginning, I'm just going to remind you about charge transport in OLEDs, which will give you some information about why we design the materials that we'll be looking at. I'll define what a dendrimer is, and then see how the structure 10 shows fits into the picture. And then we're going to look at charge transport in two different types of dendrimers, and they're defined by their dendrons, not their dendrons, but just their dendrons. And there'll be two families, one which are based on biphenyls and the others which are based on carbozoles. We'll have a look at that. And what I hope to leave you with at the end of the talk is sort of some thoughts about how you can investigate charge transport. We've looked at energy transfer and charge transport in biological systems, and they're actually very difficult to study because they're either in a very large framework or they're in floppy framework, and so it's quite hard to probe. And what we've been able to do, or hopefully I'll be able to show you, is how we can use rigid dendritic architectures to actually study the process of charge transport in well-defined systems in the solid state. So that's kind of a bit of context, I guess. So this is a slightly different picture that I showed you earlier in the week, but it is also an OLED, an organic light emitting diode, and this is the context that we've been studying charge transport in dendrimers. And I don't really want you to worry too much about it, apart from the fact that you have your cathode and your anode, which I showed you in the simple structure earlier, and then we have all these other layers in the device. And so we have these things which are electron transport layers, we have the whole transport layer, and in the emissive layer we often have the emissive component, which is a small molecule, mixed with a host. And all those different components within the device are designed to control charge transport. Okay? It's to get balanced charge injection from the cathode and from the anode, to get it all quickly through the device and ending up in the emissive layer, and then in the emissive layer end up on the emissive component to give the light out. And so to get these sort of devices to work really well, you have to have balanced charge injection and balanced charge transport. Now that's not to say that you have to have very good charge transport, you've just got to have it balanced for these types of devices. So for good charge transport for organic chromophores or chromophores which are complexes, you actually need to have them very close together. Okay? And the closer together, the better the transport. Now in terms of OLEDs, there's a problem with that because the things that often transport the charge are also the things that emit the light. And so you have this sort of tension between charge transport, good charge transport, and light emission, because if you bring two emissive chromophores close together, then you form excited state dimers, and you lose your, you end up with a redshift in your emission and a lower photolysis quantum yield. And that's why people often blend these small molecule emissive components with a host component. So in our work, what we've tried to do is say, well, how else can we control those intermolecular interactions that govern our charge transport and light emission, and that's where we get on the dendritic architectures. So what is a dendrimer? Well, this is a much simplified structure compared to one Ken showed, but basically dendrimers are comprised of three main components. At the centre there's a core, and that core could be a chromophore or it could be just an atom or a group of atoms. So in the structure that Ken showed, the core would have been, I think, just a nitrogen atom. And then attached to that core you'll have one or more branched units which are known as dendrons. And so in the Pan-Am dendrons, they're saturated ones, they all branch out via amine units and so on. And then at the ends of the dendrimer you can have surface groups. And so in the structure that Ken showed, surface groups were porphyrins. So in the materials that we've been looking at materials which have got conjugated dendrons, that is to say we have aromatic units all linked together. And one of the nice things about making dendrimers, although the structures look very complex, they can actually be made in a fairly straightforward way. Because what we can do is we can create the dendrons first and have reactive functionality at their foci, and at a late stage in their synthesis add them to different cores. And so what I've illustrated here is effectively two dendrons out of our dendron library. We have these biphenyl-based ones and these carbozole-based ones. And then in the core library, we have various emissive components. So here we have a green emissive iridium complex, here we have a red one, and here we have a sky blue one. And what we can do is we can add these dendrons to these cores at later stages in the synthesis. Now, I'm not going to go through the synthesis of these things, although if you want to, I can tell you how we make it later on. So what we're going to do is we're going to compare the properties of dendrimers comprised either of this type of biphenyl dendron or this carbozole type dendron with this green emissive core. Okay, so that's what we're going to be looking at today. So in terms of charge transport, you have to ask a little bit more about the structure. And earlier in the week, I was asked, what's actually the three-dimensional structure of these compounds? And because I always draw them flat, because if you draw them three-dimensionally, that's a real pain. But we have done some modelling of them, and this is a three-dimensional structure of this first-generation dendrimer. And it's known as a first-generation dendrimer because as you go out from the core, you reach this benzene ring here, and that's the first branching point that you have. And so you just have one branching point until you go out, and then you have your surface groups here. And these are just our epoxy surface groups. This second-generation dendrimer is the second-generation dendrimer because as you go out from the core, you get to this first branching phenyl ring, you get to the second branching phenyl ring, and then you get to this phenyl ring, and then the surface group. So we have the first and second generation dendrimer. And you can make higher generations if you really want to. But from a manufacturing point of view, if you can pack everything into low generations, it's a good thing. Anyway, so what we're going to use is these biphenyl-based dendrons, so it's the first generation and the second generation, to illustrate how we can use the structure to control charge transport. So the first question is, with this sort of dendrimer, where does the charge get injected into? And to do this, we use electrochemistry. So for those people who are not familiar with electrochemistry, this is a cycle called chemogram. And basically, as you see, wherever you see a peak, there's some sort of electrochemical process going on. So if we go from kind of around 0 volts now this way, what we see is we see a peak, and that corresponds to, as we go out, we see a peak, and that corresponds to an oxidation of a species to form a radical cation, and then as we come back, we see the reduction of that species back to a neutral species. So wherever you see this sort of flying duck, it sort of indicates that there's an electrochemical process that's going on. So I'm standing in the way, aren't I? Okay, so for this particular dendrimer, with the iridium complex at its core, what we see is we see one electron oxidation, and then as we go out, we see 1, 2, 3, and the reverse one's a bit harder to see, 1, 2, 3, so they're kind of elongated flying duck swans perhaps. And so what we can say is that this complex, so this dendrimer is undergoing one electron oxidation and 3 1-electron reductions. Of course, the question is, where do those electrons come from, where they go to? And the simplest way of doing that is to do a comparison with just a simple complex. And so you can see here is this redox results, or the electrochemical results for the complex. And you can see the oxidation occurs at 0.26 volts, similarly for the dendrimer. And on the reductions, we're sort of basically in the same position. So what that's saying is that for this dendrimer here, the charge gets injected into the core and not the dendrons. So the dendrons, if you like, are electrically insulated and acting in rigid structures. So if that's the case, and we have a film of the materials, then as the molecules get larger, i.e. as we go from the first generation to the second generation, then the cores on average will be held further apart. And so we can measure the hydrodynamic radii. In the first generation dendrimer, it's 10.2 angstroms, and for the second generation, it's 13.3 angstroms. And what that means is, as I said, on average, the cores are held further apart. If charge is injected into the core, you expect it to hop from core to core. As the cores get further apart, then the charge mobility should decrease. And that's essentially what we've seen. So the first generation dendrimer is the whole mobility is measured by charge generation times flight measurement with Heinz Bessler. And the second generation, you can see the whole mobilities here. You can see across a range of fields, the whole mobilities of the material, the charge transport for the first generation is higher than that for the second generation. So that fits for a hopping mechanism across the device, across the film. And this has some quite interesting outworkings in the device structure itself. So if you just make a simple single layer device where you put the first generation and the second generation dendrimer into it, what you find is the current density at a given field is decreased. So this is the current density of a single layer device which has got the first generation dendrimer in it, and you can see for the same field the current density for the second generation is significantly less. So we've slowed the mobility of the charges right down. And that actually has a pretty dramatic effect on the efficiency. So this is the number of photons you get out of the device versus the number of electrons that you put in. And you get a 10-fold increase in the efficiency of the device simply by essentially slowing the charges down. If you actually blend, say, the first generation dendrimer with the host material which I showed you earlier, then you can see for a given field the current density decreases significantly as well. And I'll explain why that is in a minute, but when you slow down the holes in this case, in this particular device, sufficiently, then the efficiency of the device can increase significantly again. So you get an 8-fold increase in the blended system. So the question is, how do we understand that? Well, again, what we do is we do electrochemistry on these things, and what we use the electrochemistry to give us is to give us some relative energy levels. And so what we find is the LUMO of the dendrimer and the HOMO of the dendrimer sit inside that of the host, and so charge basically gets trapped on the dendrimer in the host system. And we've measured the mobilities of that sort of system, and this is just sort of a snapshot, a bit of a summary. So what we have for the first generation dendrimer at a particular field, we have a mobility of around 4.1 times 10 to the minus 5 centimeters squared per volt second. We go to the second generation, it drops almost by an order of magnitude, and we make a blend, and it drops by an order of magnitude again. So we can control the mobility either by generation or by blending. So that's quite interesting. And this really just summarises this sort of family of materials. So basically in terms of first generation, second generation blend, what I haven't talked about is that the film PL quantum yield actually goes up a bit as we go across the series. The mobility goes down and the device efficiency goes up. Okay, so that's quite a nice story that seems to fit fairly well. So what we then wondered was, since most of these things worked quite well when you put a host in which had these carbozoles, what happens if we actually add the carbozole to the dendritic structure? Seems kind of logical to do. And so what we thought we'd do is we go from this biphenyl-based system to this carbozole-based system. And so the question then is, how many carbozoles do you need to put on? And so what we did is we looked at the literature, and it turns out that the most efficient devices made of these sort of phosphorescent complexes, the most efficient OLEDs, have about 6 to 8% of the complex in the host, which works out about 4.5 moles percent. So in terms of our first generation dendrimer here with the biphenyl dendrons, then the complex, if you like, makes up about 31 mole percent. And if you do the equivalent first generation one with the carbozole, it's 25. And so if you get to the third generation, you get down to about 6 mole percent. So this is pretty close to essentially what you would have in a really good blend device. And the question, of course, is, can you make these? And the answer is yes. Have a nice, fantastic effort. And you can make these third generation dendrimers in about, what was it? About 7 steps, 7 or 8 steps in the end. I mean, it was really came up with. So the next question is, where does charge get injected to? Well, this is the original dendrimer I showed you. We saw an oxidation, a single oxidation, and this is the electrochemistry of this particular dendrimer here. And you can see it's much more rich in electroactive species. There's a lot more going on here. And at first sight, I sort of think, that's quite interesting. So perhaps it just all goes, when you oxidize the material, you just oxidize the core, because effectively the potentials of these two oxidations are pretty similar. And so, perhaps everything will be exactly as we saw before. As we go up the generations, we see a decrease in charge mobility, and there'll be no difference. So what we did is we measured the Hall mobilities in these materials using, again, the charge generation time of flight technique. And what I've got here is a comparison. And what I've tried to do is to get as close a field as possible to the field that we use for measuring these materials here. But what's really interesting is that as we go from the first generation of this material to the second generation to the third generation, the whole mobility increases. It doesn't decrease this time. And that's really curious. And what's more is the mobility of the third generation is significantly higher than the first generation material here at a lower applied field. So it's actually better than better, if you like. And again, just to remind you where we are in terms of the second generation dendrimer, it's really more than an order of magnitude lower than the second generation carbozole. So something completely different is going on here. You have to understand that. So what's going on? Well, if you just go back, you might sort of naively think, well, you know, we've got these more electroactive species, so perhaps all that's happening is each dendrimer can cope with having an extra hole on it, and so we're sort of not restricting ourselves in terms of charges on a particular material. The problem with that is that the potential of the second oxidation is sufficiently higher in energy, if you like, than you would actually get in a thin film with the field that we put across. So that can't be the answer. It's getting more than one charge on the structure. And so what we had to do is to go back and consider the molecular orbital distribution of these dendrimers. This is what we've done. This is done by Chris Shipley again. And so what we've done is we've calculated, sort of in a target diagram, the molecular populations of the frontier molecular orbitals. And I've got them here as a percentage. So if we just consider the highest occupied molecular orbital rather than the lowest unoccupied molecular orbital, it's slightly less interesting, but we can talk about it later if you're interested. Basically, in terms of the complex, so that includes the iridium and the 2-phenylpyridyl ligands, you can see round about 94% of the orbital density sits on that central component, that central core, okay, which fits with the hopping from core to core to core through the film. And there's only a very small percentage actually on the dendron. And so that, again, fits with this whole hopping mechanism that we saw earlier, and going from the first generation to the second generation, the whole mobility, or the charge mobility, decreased. As soon as we put the carbozole on, though, the picture changes completely. So what we now have is the same sort of target diagram, but now we actually have 40% of the homodensity sitting on the carbozole units. And so we've redistributed the highest occupied molecular orbitals in terms of where they are on the complex. If we go from the first generation to the second generation, then what we observe is we still see a significant amount of homo-orbital density on the outer carbozoles. And what's happening effectively is we're bleeding it away from the iridium complex at its core. And so that's fine. What about the third generation? Well, in the third generation, we still have a significant amount of highest occupied molecular orbital density on the outer carbozoles. In fact, we've got very little localized on the complex. So we can understand the improved charge mobility, because as you go up in generation, you actually have a lot more chance of overlap of highest occupied molecular orbital density, because you have a lot more units over which it's distributed. And so that's why you see the opposite effect with these materials to the biphenyl materials, because the molecular orbital is distributed over the whole complex. So what happens in terms of devices? Well, this is the slide before the summary slide. So what we did is we took a material which had effectively the same pL quantum yielding in solid state, and we knew the mobility. So here the mobility is just about, well, it's twice that of the first generation material here. And if you just make a simple device out of this one, then you can, a simple bi-layer device, so we have our dendrimer, an electron transport layer between the anode and our cathode, then you get an external quantum efficiency of about 9%. If you take this material, then it drops down to around about 3%, so it's worse. Okay? So the whole transport is better, but the devices are worse. And the reason for that is the whole transport is now too good. And if you actually mix this dendrimer with a host material, so you're now getting the charge trapped on the dendrimer and you're slowing the charges down, then the device is actually improved. So, summary. The summary is, for this class of materials, as you go from first, second, third generation, film PLQY increases, the mobility increases, but the device efficiency is actually worse than the equivalent biphenyl-based dendrimers. So just to conclude, I hope I've shown you that you might think that dendrimers I hope I've shown you that I think dendrimers are really kind of a neat architecture to study this charge transport, is we can design not only the intermolecular interactions by generation, but we can also do it by dendron type as well. And I think one of the key things from the optoelectronics field is that we can really tune the charge mobility for a particular device application. So I'll just leave it there. Thanks.
Is the problem of your mobility being too high to make the mobility higher of the other charge carrier to match?
Yeah, that in principle you could do that. But what's kind of so essentially what's happening, I think, is that there's an interface here between electron transport hole blocking layer. So this material transports electrons and blocks holes. And if you get the holes all racing across and they hit there, then all the excitons are actually formed at that interface. And as soon as you get all the excitons formed at that interface, there are other quenching processes that go on, because it's a phosphorescent system, which means the lifetime's fairly long. So the question is, if you sort of make that work really well, can you solve that problem? I think to a certain extent you might be able to, but to a certain extent you'll be dependent on the lifetime of the exciton. So what's probably better is to get a sort of graded exciton formed, sort of across a gradient in the layer.
What do you get the emission from the carbozole?
You don't, and that's another story. So, so I mean, it's a really good question. So, what does the emission of this look like compared to this? So, if your HOMO is delocalized, then you could argue that the whole energy system would sort of decrease, and this would be redshifted. In fact, you still get green emission. And I think what happens is when you form the excited state is actually highly localized. So, we've been effectively looking at the ground state, but when you form the exciton, it's highly localized back on the center of the dendrimer, and so you only get green emission, which is really curious. So, I mean, I don't fully understand that.
But isn't that because your LUMO is very localized?
Yes. So, the LUMO is localized on the two-channel period. So that's probably the driving force to make sure that the hole ends up there.
Just what I mean, have you inadvertently made a delocalized system with your carbozole dendrons, where your you've got a meta substitution pattern which delocalizes or localizes rather. So I guess what you're after in select transport is non-conjugation as such. So your phenol ones there,
yep.
Phenol then
yep.
Your carbozole is good enough to localize the system.
Well, we deliberately, I mean, with the biphenyl ones, we deliberately put that meta branching in because people have tried to mix phosphorescent materials with conjugated polymers, and apart from red, that's a bit of a disaster. And the reason for that is the triplet energy of most conjugated polymers decreases very rapidly. And so as soon as you have something which is not a blue emissive polymeric system, then you start quenching the triplets and you form the phosphorescent. So for red, it's okay to get away because the triplet energy of a red phosphorescent material is lower than that of a polymeric system. So with the blue polymeric system, but by having these metal linkages, we deliberately disrupt it so the triplet energy, if you like, the lowest or the biggest triplet energy in our dendron is really of that alkoxy biphenyl. So that was deliberate.
Could you do a similar thing with your carbozoles to break the conjugation by physically having them rotate so that in subsequent iterations are now 90 degrees, so you put metals on the previous generation?
Yeah, in principle you could. I mean, if you had, I mean, it would actually be, from a synthetic point of view, it would not be trivial to do that because you would have to introduce functionality here and here, and then on your basic carbozole, so you don't have a bromo. Well, from a synthetic point of view, you'd have to do that. But in principle, you could do that to pause the twist to increase the to break the conjugation.
What reaction do you use to
put these together? I mean, it's palladium chemistry, and I mean, the fantastic thing about the chemistry that the guy worked out was basically you take this component here, so you can buy effectively the dibromo carbozole, so there's bromine here, and in a simple reaction you can put on these surface groups, and then what you can do is you protect the nitrogen, and you have bromine, protected nitrogen, and you sort of play the catalyzed coupling with heat protection, play the catalyzed coupling with heat protection, get your different generations, and then when you've got a heat protected nitrogen, you just take the complex which has got bromine here and do the same reaction. So the whole molecule is basically put together by two reaction types. It's really cool chemistry.
I have one question. You looked at mixing the biphenyl dendrimers, and you mixed first and second generation dendrimers. Is that right? And then you had, so there was something a little bit unusual, that the efficiency of the mixed one was actually better. Am I getting that right?
Yeah, you are. So what we did is we took, so what we took is we took this compound, this one here, the first generation dendron, and we mixed it with this material here. So we had a guest host system, and what happens in that situation is that the charges go even slower, and the flip side is that the efficiency increases,
and it's much more efficient.
And you could argue, well, actually it's much more efficient because it's got a higher photoresistance quantum yield. But the difference in photoresistance quantum yield between the first generation and second generation of the blend is not such that you can take into account the higher efficiency that you observe in the devices. So it really is controlling the charge ability through the devices.
What is the practical efficiency of the these things? You need it better than 80%.
Yeah, the higher the better. I mean, if you can get 20%, then everyone will be very happy. 20% is the maximum you can possibly get, because, well, depending on the outcoupling of the light from the front of the device. So if you have 100% internal quantum efficiency, and the outcoupling is generally assumed to be around about 20%, a fifth of it. So if you can get 20%, that's really good. In terms of green, for the small molecule ones with these huge, these great numbers of layers, different materials, people have basically got 20%. Best we've got is 16%, but they're in much simpler device structures. So instead of having sort of, I think it's generally 5 layers, 6 materials, we can get 16% out of 2 layers and 3 materials. So from a manufacturing point of view, it's actually much simpler. And in fact, we've had 13% out of 2 layers and 2 materials. So by careful design of your materials, you can make the manufacturing process a bit more simple. But yeah.
This might not be an interesting point, but what's the significance of the hysteresis in the cyclic photograph?
Oh, that's diffusion control. So if you had effectively, if you look at electrochemistry which is not in solution, it's on the solid and it's reversible, then your oxidation and reduction fatigue will be at basically the same position. So these are done in solution. So there's now a diffusion control there.
Okay, well, I think we've done very, very well with questions. It just remains to say thank you. And to introduce the last speaker for this morning's session. And Colin has already given us a talk on probing the water on the surface